The question here is, what is theory of compaction? This is something that applies to soil with fines. In an earlier video, we talked about compacting granular soil, right? So as soon as you have some fines, you are introducing cohesion into the soil, and then it turns out that vibratory loading, which works very well in densifying sandy material, or pure sand actually, doesn't work very well here anymore. On the other hand, impact loading, like the one from dropping a hammer, or static loading, like pushing it down, work very well. Then the question is, do we compact the soil completely dry, or do we compact it with some water in it? It turns out that you cannot effectively compact the soil when it's completely dry. You need to have some water in it. Water lubricates the particles and allows them to be densified. The next question is, how much water? So objective is to bring the particles as close as it is desired, right? Another way of saying that is we want to reduce the void space in the soil. From what we learned earlier in the section on weight-volume relations, we know we can use either the void ratio or the porosity to quantify the void space in the soil. And there's a third way too, which is a little bit more practical. That is to use the dry density as the measure of the amount of void space we have in the soil. Remember this relation? The total unit weight and the water content can be easily measured in the laboratory, and then you can calculate the dry density from this equation. If you were to compact the soil at different values of water content and plot a relationship between the dry density and the water content, this is what you will get. So as the water content increases, the dry density will first increase and then it will start decreasing. The value of the water content at this peak point is called the optimum water content. The value of the dry density at this point is called the maximum dry density. Let's say we got this curve from 7 different tests. Let's say in all 7 tests, I maintain the same compaction effort, which I will define in a little bit. Then it turns out, number 1, you will get a smooth curve like this. Number 2, this is the water content that's going to give you the maximum dry density, which of course corresponds to the maximum possible packing of the solid particles. So this answers our original question of the amount of water that leads to effective compaction. This is the answer. Let me now talk about compaction tests that we do in the laboratory. Let me start with the standard Proctor compaction test. So here are some pictures showing the equipment needed to do this test. So what you want to do is to take a certain amount of dry soil and mix it with a certain amount of water, and keep the amount of water small for test number 1. Then you want to compact the soil in this cylinder called compaction mold in layers using this hammer. And this is a standard test, and the specifications are given in the ASTM manual. Everything is standardized. The hammer looks like this. You raise the weight by pulling this handle up to here and then drop it. The mold has 2 halves. The idea is that once you're done with compaction, you want to have the soil sticking out a little bit of this bottom half. Then use this straight edge to cut a flat surface at the top. The dimensions of the cylinder and the hammer are all standardized. Even the weight is standardized. And in this test, which is the standard Proctor test, you compact the soil here in 3 layers and you apply 25 blows for each layer. The mold has a known volume. If we can get the weight before and after compacting the soil, we can get the total weight of the soil. Divide one by the other, we get the total density. Then you take a couple of small samples of soil from this compacted soil and place them in these little containers for measuring the water content. First you weigh them to get their wet weights, and then place them in an oven over a period of 24 hours. Weigh them again to get the dry weights. And from the two, you can calculate the water contents. You use a couple of different samples so that you can get an average value of the water content, because the water content kind of varies from point to point within this compacted soil. So from the total density and the water content, then you can calculate the dry density. So for this test, we have the dry density and water content, right? Then you take this soil out, add a little bit more water, and repeat the whole process. So you have another pair of dry density and the water content at a slightly higher water content. And you repeat this process a number of times in order to get a smooth dry density versus water content curve. Remember I mentioned the phrase compaction effort, right? I was going to come back and explain that to you. So what does it mean? So this picture right here summarizes the variables associated with the standard Proctor compaction test. The drop height is 12 inches, weight is 5 pounds. We compact the soil in 3 equal layers, and for each layer we apply 25 blows. And this combination represents a specific level of compaction effort. So basically it's the amount of energy that you put into the soil in order to compact it. So let me compare these with the variables associated with the modified Proctor compaction test. The drop height is 18 inches, the weight is 10 pounds, we compact the soil in 5 equal layers, number of blows remains the same as the one in standard Proctor test. So this combination represents a higher compaction effort. So this is the result. If you get this from the standard Proctor test, you're going to get this from the modified Proctor test. So let me talk about a few other related aspects here. First, let's talk about what is called a zero air voids curve. So now we know a typical dry density versus water content curve looks like this, right? And this curve corresponds to a particular compaction effort. So for this compaction effort, if the water content is omega 1, gamma sub d1 is the dry density that you're going to get. We also know that if we take the same soil and increase the compaction effort, the dry density is going to go up a little bit, right? It's going to go over here. So how did that happen? Well, some of the air in the voids came out, right? So you can see that if I keep increasing the compaction effort, at some point, all the air in the voids would have come out. We will have a state of zero air voids. Say this point right here represents the zero air void state for this water content. The soil is now fully saturated. So if I repeated this for different water content, I'll get these points, and if I connect all these points, I'm going to get a smooth curve. And this is what is called the zero air voids curve. So it's natural to ask whether it's possible to calculate this theoretically. The answer is yes. So the derivation starts by recognizing the fact that the soil is now fully saturated. So here are the steps in the derivation. Remember the phase diagram that we used to derive the weight-volume relations? So this phase diagram is for a fully saturated soil. We have the volume fractions on the left side and the weight fractions on the right side. I didn't put anything over here because we are only interested in the dry soil. So when the soil is dry, this would be occupied by air, and we neglect the weight of the air. This is the relation we had for water content, if you recall. But in our case, the degree of saturation is 1, and therefore water content simplifies to this. By rearranging it, I can express the weight ratio in terms of the water content by this relationship. So now we come and write down an equation for the dry density, and I would call this dry density as gamma sub ZAV, ZAV for zero air voids. And on the right hand side I have the weight, which is GS times gamma W divided by the total volume 1 plus E. And by substituting this for the weight ratio, I now have a relationship between the zero air void density and the water content. So this is that relationship, and in this relationship, if you notice, everything I have on the right side is a constant except for the water content. So we have a relationship between zero air void density and the water content. So I can plug in different values for water content and calculate the corresponding values of gamma sub C AV and plot this curve theoretically. Another point that I want to make here is the following. On the right hand side of this equation we have G sub S and gamma sub W, right? So these are the two constants. Gamma sub W is the density of water, which is a constant. G sub S obviously varies from soil to soil, but it always lies in a very narrow range between 2.6 and 2.8. And therefore, this curve here is approximately a constant for all the soil. So let me use these experimental curves obtained for a bunch of different soils to make this point and a few other points. So we see that the zero air voids curve is approximately the same for all 8 soils. Another point to note here, which we discussed back in the section on soil classification, that well-graded sandy soils 1 and 2 achieves much higher dry density than the poorly graded sand soil 8. So this is because a well-graded soil has a little bit of everything, and the smaller particles are able to get inside the larger pores between larger particles, yielding higher dry densities. By the way, these are not purely sand, these are sands containing some fines in them. Another point to note is that the dry density decreases with increasing plasticity. This heavy clay, which has a very high plasticity, lies almost at the bottom. Finally, as we would expect from these discussions, all compaction curves lie below the zero air voids curve. So these are basically the details of the theory of compaction. For a given compaction effort, there is a unique relationship between the dry density and the water content. As the compaction effort is varied, this relationship varies like shown in this picture. The curves associated with higher compaction efforts lie above the curves associated with lower compaction efforts. All of these compaction curves, that is the relationship between gamma, d, and omega for various compaction efforts, all lie below this curve called zero air voids curve. This is a theoretical fact because a point on the zero air void curve represents the state where there is no void in the soil. So the dry density of the soil cannot be more than the dry density associated with that state. So what about the relationship between compaction and properties such as strength, permeability, etc.? It turns out that we need to throw in one more variable in the mix, which is the structure. Now remember, we talked about this before. Something like this is called the flocculated structure and something like this is called the dispersed structure, right? So let's look at these one at a time. First, the strength increases with dry density. So if I go along this compaction curve, the strength is increasing until this point, and then it's decreasing because the dry density decreases after that. So if you look at it purely from a dry density point of view, you would think that these two soils, soil A and soil B, will have the same strength because they have the same dry density, right? But it turns out that's not true because soil A tends to have a flocculated structure, whereas soil B tends to have a dispersed structure. So here is a comparison of the stress-strain curves for these two soils, and the soil with the flocculated structure tends to be a little stiffer, so its peak strength is a little higher than the peak strength for the soil with the dispersed structure, but they all tend to reach the same shear strength in the end. As we touched on a little bit earlier, the structure also influences the permeability. Permeability of flocculated soil tends to be higher than the permeability of dispersed soil. And therefore, the permeability at point A will be higher than the permeability at point B. But we want to be careful with this type of simplistic interpretation because the structure also depends on the method of compaction.